Okay, recording. And just a heads up, I won't be able to see the chat, so I only see it when class is over. Really defeating the purpose. When I teach online, I have two screens. I can watch the chat here and I can do it here. Here I can't. All right. So what were we talking about? Oh yeah, we were talking about different distributions. Please. Thank you. We'll see if anyone else shows up. We were talking about some distributions, really only because we might find it helpful to have a good handle on some of these most common distributions. So we started talking about, we kind of went way back and talked about the normal distribution. And then we said, okay, well, usually things aren't necessarily normal. And so let's talk about some other distributions today. I'll kind of just talk about each one pretty briefly, just the things you need to know, right? And then I think it's in chapter 3, so the next chapter, then we start doing some hypothesis tests with these distributions. So we're just introducing them and then forgetting about them for a little bit. So we were discussing some common distributions. There are lots of other distributions, but these are the ones to kind of keep handy. And so in general, when we said that, okay, it's pretty rare that things follow a normal distribution, a strictly normal distribution, what's more common is that we have these long tail distributions. Yeah. And so let's talk about long tail distributions. And I'll highlight. Can't remember what I've been doing. I think I'm highlighting all the different sections, but I can't remember. The normal distribution, like I said, rarely applies to raw data. It's me. Put it in here. To raw data. Yeah. We often see these long tail distributions, which if we think back to the tails of a normal distribution, those are the more extreme outcomes, right? So if we have longer tails than we're expecting, that means that we're seeing more extreme things than were originally expecting under a normal distribution. Okay, and so we often see long-tailed distributions instead of perfectly normal distributions. So in terms of the distributions, if I draw them here, so if I start with a perfectly normal distribution, I'll do my best. Here we go. Might look something like this. I'll draw this line here. Whereas a long tail distribution is going to have more thickness in the tails, right? Because they go further or longer, which means they tend to flatten out in the middle. Oh, I gave myself too much lift here, but I think you get the idea. Oh, okay, fine. Try again. something like that. Okay, that's pretty good. Remember, the total area is still 1 under the curve. And so if I have more in the tails, then the bottom or the top kind of gets squished down. And if I have tighter tails, then it works like this, right? So that's why it's squished down. So what does that mean in terms of probabilities? Okay. So what does this mean in terms of probabilities? Right. If probabilities, and they're the areas under the curve, right? Then what I'm saying here is I'm allowing for more of a probability, a higher probability of these extreme things happening in a long tail distribution than under the normal distribution. So if things kind of naturally happen with this long tail distribution, right? But I'm assuming that it follows a normal distribution, then all of a sudden I'm going to have all these rare things or seemingly rare things happening when I need to assign a higher probability to those things, right? So we need some way to work around that. But first, let's say, so recall, oops, the area under the curve is a probability. So what we're seeing here is there's a higher probability of extreme values in the long tail distribution. In the long-tailed distribution.
Yes. Yes.
So like I was saying, when we have a long-tailed distribution, then if we're working under the assumption that it's a normal distribution, then we're going to be thrown for a loop a lot, right? Because we're seeing these extreme things that aren't necessarily extreme, right? And so in a long-tail distribution, or in long-tail distributions, extreme values are more likely than expected by the normal distribution. Than expected, maybe I should say under the normal distribution. Under the normal distribution. So one of the more famous long-tail distributions is the t-distribution, which we also call the student's t-distribution. And you've probably heard about the background of the student's t. His name was actually William Gossett, and he worked for this Guinness brewery, and they wouldn't let him publish his paper. So he had done all this research, but they considered it top secret, so he wasn't allowed to use his name. So he published under student. So that's why it's called student's t-distribution. But he basically went through and did exactly what we're going to be doing with bootstrapping, is he just pretended to take a bunch of random samples and watched how the distribution kind of happened. And they show it in the textbook as well. Oh, and I guess on the slide, I did find a PDF. I can't remember if I told you guys, I stumbled upon a PDF of the textbook. So I don't know if I can post that because I don't know, but I can post the link if anyone wants the link to the PDF, or you might just be able to find it. But here's the textbook. So here's what he did. That'd be so tedious. right? Oh, I'm going to randomly select a random sample, right? But kind of fun. So the student's t-distribution, and we've used the t-distribution, right? As soon as we were doing hypothesis testing about the mean, then we use the t, right? Student's t-distribution. So anytime we had to test the mean, we can also use the t-distribution for a lot of other things. We can test the correlation. What else? So this is slope. The intercept is kind of boring. Lots of hypothesis tests that we can do with the t-distribution, and it applies, right? So that's nice. And how we arrived at the t-distribution was very similar, right? Depending on our sample size, that would kind of make more room in the tails, right? Make more room in the tails if we have small sample sizes. And then as we increase our sample size, well, then our sample is slowly morphing into our population. So then it becomes the normal distribution, standard normal distribution. So the t-distribution is shaped similar to the normal distribution, but has thicker and longer tails. Is shaped similar to the normal distribution, but has thicker and longer tails. Which means that really what you're doing is you're increasing the probability of these kind of extreme values, right? Which means that this increases the probability of extreme values compared to the normal distribution. So they're basically the same, but the t-distribution relies on the degrees of freedom, right? And depending on what type of problem we're applying the t-distribution to, right, that's going to determine the degrees of freedom. But the t-distribution changes, I think of it as changing shape, right? If it kind of lifts in the tails or not. So the t-distribution changes, I'll kind of say shape, which I really mean the tails, depending on the sample size. Or maybe I'll say depending on the degrees of freedom. Let's just call it what it is. You guys are ready for that. Right. Which often depends on the sample size. Degrees of freedom often depends on the sample size. Right, for example, n-1, right? For a one sample mean hypothesis test or confidence interval, for example. So we're going to see a lot of t's in our output, right? If I run a regression in R, then of course it gives me t's. So we need to have a pretty good understanding. But like I said, we're going to save that real understanding for chapter 3, where we actually use these distributions. All right, until then, what's another distribution that we've seen before? We talked about the binomial distribution. Binomial distribution is for 0, 1, or binary outcomes, right? And so that's our next one here. It looks cramped because I've got a page break here. Binomial distribution. We've worked a little bit with the binomial distribution, but it was a long time ago, right? And so just as a little refresher, we can only have two and only two possible outcomes. So usually we call these 0, 1 outcomes. So things like yes, no, success, failure. Kind of a cop out, etc. Right, and so here, call these 0, 1 outcomes. The 1 is used to tell you which thing you're interested in, right? The thing we're interested in modeling becomes the 1. And that depends on the question that you want to answer. So it's not always that the yeses are 1s and the nos are 0, right? But in general, a success is the thing that you want to talk about. Where 1 is used to denote the outcome of interest. Often this is going to be a rare outcome. That's what we're kind of interested in. When does this thing happen? Right, so often a rare outcome. Because if you think about it, if an outcome is pretty common, then we could just look at information and get a pretty good handle on how often it would happen, for example, right? But usually we're trying to model these rare outcomes. I don't know if I wrote it down. Where did I know I saw it. I just can't remember where I put it. That's okay. Continuing my list way down here, I guess. Oops. These outcomes have to have fixed probabilities. Okay. The two outcomes must have fixed probabilities. Otherwise, we can't use the binomial. Oh, totally random, but I was just thinking about it. Not sure why. I think I made the lab 2 or whatever number it is due tomorrow, but I can move it. I don't know, I can move it to Monday if you want. You guys, whatever. I don't care. Thank you. I'm usually pretty open to moving stuff if you guys just let me know. And I know that's bad. But lab 2, I'll put it at the top here. I will change the due date to Monday night. How about that? And just as a note, I want you to submit just your RMD file, or if you prefer LaTeX, your RNW file. So I don't want the PDF, I want the RMD or RNW file. Yeah. And then I'll run it on my machine and just kind of make sure that it's all tickety boo. Okay, good. Yeah, I knew there was something. I need more space here. There's also an assignment that I think I made due tonight. That's rude. We never talked about it. I just put it up there and I saw some people have finished it and that's awesome. But same thing, I can bump that due date just in case it's stressing anyone out. Assignment, I think it's just called Exploratory Data Analysis. Will be moved to Monday as well. If you've done it, that's great. Then you don't have to worry about it. But if you haven't, I know you guys have a lot of stuff going on. It's just a bunch of multiple choice questions because I'm not that creative for chapter 1. I think you get 4 attempts, but after 2, because they're multiple choice, it starts penalizing you. Seems fair, I think. Okay. I knew there was other stuff I wanted to talk about. All right. So just as a reminder about the binomial distribution, it's a frequency distribution, so we can use it to find probabilities of certain successes and failures. And so the binomial distribution is the frequency distribution of the number of successes which I usually denote X, in a given number of trials, in a given number of trials, which I usually call N, right, in N trials, with some specified probability of success, which I call P, in each trial, with a specified probability of success in each trial. Now, right, you might remember, I'll put it in brackets because we're not going to use it again, right? Because we're just going to get R to calculate these probabilities. But we did use things like the probability that X equals X is N choose X times P to X times Q to the N minus X, right? But we're going to use R to calculate these now. Yeah, this one's a lot easier. Once you get it, it's like, oh, okay, yeah, I got it. Takes a little bit to get used to, though. We will use R to calculate these. With the binomial problems that we've done in the past, there were a couple of different problems that we could ask, right? We can find the probability of exactly some number of successes, right? Or at least some number of successes or more than some number of successes. But the exact probability, when we're finding that, we call it the PMF or the PDF, the probability mass function or density function. I think it's density function. I usually just distribution function. So we can find the probability of exactly X successes right, which is the same as the probability that X equals X. We're going to start calling this the PMF or PDF. Usually I call it the PDF. That gets confusing though, because yeah, which I can't remember what the document type PDF, what does that stand for? Portable document format or something like that, I think. Did you guys know USB? Pretty sure it stands for Universal Serial Bus. Yeah, like a USB stick. I'm reading this like beginner textbook on Python. Okay, fine, it's for like middle school kids, but it's like, it's pretty fun how they've laid it out. I saw it at Costco one time and I was like, is it a universal serial bus? See, I remembered something from my little kitty textbook that I'm reading at night. I'm like, ooh, oh, cute. Oh. But I guess eventually they're going to teach me how to code in Python, so can't wait. Anyways, if it's any good, I'll share it with you guys. Okay, so the PMF or the PDF, which is the probability mass or distribution functions. They're the same. Just some textbooks call it the PMF and some textbooks call it the PDF. That's fine.
How did you learn Python? How did you start?
Well, I'm reading this kitty book right now. It's like, it's called something like coding for middle schoolers. I have no idea how they would wrap their heads around this stuff, but whatever. I know. So yeah, when I saw this book at Costco, I was like, yeah, I may as well buy it. See what's going on. If it's any good, I'll bring it here and I'll lend it to you guys. Or I might steal some stuff out of there. If it's any good. I have to read. It's like chapter 7. I'm only on chapter 3 right now. Stay tuned. I have no intentions of reading it this weekend though. No, thank you. So the PMF or the PDF is when we're looking for exact probabilities. What's the probability that X equals 4, X equals 6, blah, 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 right? And the other kind of type of question that we can ask is the probability of less than and including some number of successes. Less than and including X successes. Hello? Oh, there's a chat. Oh. Okay. It was an accident. I can only assume. All right. See, I hear you if you unmute yourself, but I can't see the chat. So something like this, right? we're going to refer to this as the CDF, so the cumulative distribution function. The CDF, which is the cumulative distribution function. And if you think about the Z table, for example, the Z table gives you probabilities to the left, right? So those are cumulative distributions, right? Because it's all the values up to that point and below, right? So those are CDFs. So it's not just the binomial that we can talk about, the PDF or the CDF. All distributions, we're going to have the exact probability and then some probability up to a certain point, right? Cumulative. But it's easiest to think about in terms of the binomial. We also saw that as we increase the number of trials, right, one, it becomes kind of hard to do the calculation by hand for the binomial, right? If I have 42 trials, 42 choose, let's say 9, I don't know if my calculator is going to know that number or it's going to be too large. So then what we said is, okay, as we increase our sample size, right, or the number of trials, then what happens is the binomial kind of shifts and morphs into the normal distribution. So then we can use the normal approximation to the binomial. So as we, I'll put it on a fresh page here, as we increase the number of trials, we will find the binomial distribution tends towards the normal distribution. So this is especially true if P is close to 0.5, then it doesn't take very long for things to kind of approach the normal distribution. And you might remember there's some conditions we had to check. We had to check that we had at least 10 successes and at least 10 failures in order for this to be true. But this is especially true. How can something be especially true? It's true quicker, but that sounds weird. It's especially true when P is close to 0.5. Right, 50-50 split between the successes and failures, right? Because you might recall we had to check NP had to be greater than or equal to 10 and NQ had to be greater than or equal to 10, right? At least 10 successes and at least 10 failures. Right. This is going to be satisfied, right? NP greater than or equal to 10 is going to be satisfied quicker if P is closer to 0.5. If the probability of success is really, really, really rare, then you're going to need a very large sample to pick up some rare events, right? And so at least 10. So as you shift this point, if it tends towards a normal distribution, well, a normal distribution is going to have a mean and some standard deviation, right? Because those are the parameters of a normal distribution. And so what we use is n times p is the expected value if we have a binomial distribution. So that's what we use as the mean. And then the variance NPQ, which means the standard deviation, is the square root of NPQ. We can find, and maybe I should say we can approximate the mean and standard deviation or the variance. We're kind of grown up now, right? We can talk about the variance. It's fine. Of the binomial distribution. Mu, I'm going to use n times p, which is really the expected value of x. Expected value of x. Sigma squared, right, is the variance, the population variance. And I'm going to use NPQ, where Q is 1 minus P, in case you forgot, right? But this means that sigma is the square root of NPQ, which is what we're more used to seeing. Nice. Okay. Binomial situations, they happen a lot, and we can kind of make them happen a lot. So it's really useful to kind of know your way around the binomial. Another one that's pretty useful is the chi-squared. The chi-squared can be applied to a bunch of different situations as well, just like the t distribution. We can use the t to calculate for one mean, for the difference of two means, for matched pairs, for correlations, for slopes, right? We can use the t from a bunch of different formulas. Same with the chi-squared. So the chi-squared, this is the Greek letter chi, or my attempt at one. It's supposed to be like a fancy X, I think, like this. Or you can just write chi-squared. Chi-squared distributions are used for counts. And the reason for that is because we have methods of seeing, okay, is the mean significantly different from this number, or are these two means significantly different from each other, right? And so if we have numerical data, we have the tools to deal with that, but we don't necessarily have the same tools for counts, right? So if I have two categorical variables, then how can I tell if those things are behaving the way I expect them to? And so that's where the chi-squared distribution comes in. And we use it to model departure from expectation, okay, in counts. The chi-squared distribution is used to model departure from expectation in counts. Counts means that we have categorical data. Therefore, categorical data. So what do we mean by that? Well, we can calculate a chi-squared test statistic by hand. Of course, we're not really going to do that, but we do need to have an understanding of what R is doing, right? And if we know the formula, or if I give you the formula, then you can look at the formula and you can remember that, oh, right, I'm looking at the departure from what's expected. So I'm going to have observed counts and I'm going to have expected counts. And that's what the chi-squared does. Okay, so the calculation for chi-squareds is going to be the observed minus the expected, count. So I have some counts in some categories, right? So let's talk about grades, A, B, C. That's it. 3, that's fine. Right, and so I tell you that, oh, okay, here are the counts that I had in each category. And then I said, okay, well, I was expecting them to be evenly distributed, right? So then I have these observed counts that I can compare to the expected counts. So here, right, this departure from expectation is what we're seeing here. The observed minus the expected. There's a little bit more to the formula. We divide by the square root of the expected value, and then we square them, and then we add them all up. That's the chi-squared, right? Because each cell is going to have some observed count and expected count, and then I can do that for each of the cells. Let's write down. Consider these grades or grade distributions. Are they equal? Right, so for example, A, B, C, F. No one's in the F category. So if I tell you what I observed, I had 6 and 12 and 9 and 3. For example, right? So I had a class of 30, right? And so just looking at these, we would probably say, no, I don't think that they're distributed equally, right? There seems to be some sort of trend towards a B and a C grade, right? Or at least the upper half, right? And so what we can say is if they were distributed equally, then I would expect this 30 to be distributed equally. So now I can find my expected counts would be 30 divided by 4, which is 7.5. And it's okay to have partial counts because these are just expected counts, right? And so 7.5, 7.5, and 7.5. This is what I would expect to see if they were equally distributed. This is what I would expect to see if they are equally distributed. So now what I can go through and do I don't want to do it. Oh, good, I didn't. I don't want to do it. Right, is take the observed minus the expected. I can take the deviation from the expected value and I can divide by the square root of the expected value, and then I can square that number, and then I can move on to the next one. I can do the same thing, and then I can add all those values up. So if those deviations, right, the distance between the observed and the expected is large, what's going to happen? My chi-squared is going to be large. Okay. So if the observed counts are far from the expected counts, chi-squared will be large. How can I get there? Well, remember, chi-squared is the sum of the observed minus the expected over the square root of the expected. Right? So then if, let's start here. If this is large, right, then, well, dividing by the expectation, right, is also going to be larger, because the expectation would be the same regardless of your counts, right, your observed counts. And so then if the numerator is large, then dividing by the same number gives you a larger number. And then squaring it makes it even bigger. And then adding those up gives you a larger sum. Right. So then all of this, cut to the chase here, becomes large. Right. Same thing, if the observed minus the expected is small, right, then it's close to the expectation, and you're expecting a very small chi-squared value, close to 1. Chi-squared can be used in a few different situations. So there are goodness of fit tests, tests of independence. There's one other one. Can't think of it. There's another common one, and I'm blanking. That's okay. It doesn't matter. But chi-squared can be used in a few ways. But most often, it is a goodness of fit test. Right, so like we said here, what we were finding could be considered a goodness of fit test, right? How well do these counts fit my assumption that they're equally distributed? Right. Chi-squared also relies on degrees of freedom, but it's usually attached to the number of categories in some way. You can have one set of categories or a 2x2 table. So it depends, but chi-squared also relies on degrees of freedom, which will depend on the number of categories. So binomial and chi-squared, those are all for categorical data, right? Success, failure, counts in different categories. And so now I want to talk about the F distribution, which we really didn't get a chance to talk that much about in Stat 230. So, and we'll talk more about it. We'll use it in terms of an ANOVA, which is an analysis of variance, depending on what courses you've taken or are taking. Might have seen ANOVAs, so we'll go through those pretty thoroughly. But I think I was like, oh, and then another thing that you could do is an ANOVA. I feel like I didn't do a very good job. I'm glad you remember. I know it's one of those things that I usually don't have time to do much with. But the F distribution is usually used for the ANOVA because, and it can be used in other scenarios, but most commonly, and I think I've been doing a space here. The F distribution, when do we use it? Compares numerical values across categories, right? So now I have these numerical measurements for each category, and I want to compare the means in each of those categories typically, right? And so the F distribution compares measured continuous values so numerical data across groups. Which would come from categorical data, right? I asked that like a question, but I meant it as a statement. This is going to be different from the chi-squared, right? Because the chi-squared compares counts across groups, but now we're comparing measurements across groups. So F is approximated by the variability among the groups divided by the variability within the groups within each group. And this is typically for an analysis of variance. That's where it comes from, right? Because all of a sudden I'm comparing the variability here against the variability here. And what does the variability among the groups? So now I'm looking overall among the groups. There's variability here, right? Kind of going from group to group versus the variability within each group, right? So if you're imagining side-by-side box plots, which is usually where we start with these things, if the box plots are all nice and tight, but they're all kind of spaced like this, and there's clear distinction, well, overall, there's lots of variability among the groups, right? Some are down here, some are up here, right? So total variability among the groups is large. But then if I take into account the spread within each group, if it's small, then all of a sudden I get a large F statistic, right? So that's kind of the root of analysis of variance as we look, okay, overall, what am I seeing? I'm seeing something from here to here, kind of looking across the groups, but then within each group, am I seeing that same stretch? Because then they're basically the same, right? Or am I seeing something different? So we can use F to compare more than two group means. If we're comparing just two, right, you should use a two sample t-test, right, or a two independent samples t-test, because it's going to be more efficient. They're going to be very, very similar. The results will be the same, but there's no point in using an F if you only have two groups. So an F value close to 1 shows that there's no significant difference between the groups. Shows there is no significant difference between the groups. F also has degrees of freedom. So F also relies on degrees of freedom. Which is related to the number of groups. It's not exactly just the number of groups, so I'm not saying that, but once we do the hypothesis test, we'll see. It's a couple of sources of degrees of freedom. Okay. Long list of distributions, right? It's not really something that you have to memorize, but it is good to be aware that these exist, right? Because then if you're able to say that, oh, wait a second, if I want to compare means across multiple groups, then, oh, there's something that does that. And then you can flip back and you can say, oh, I can use an F test, right? Or I can use the F distribution. Same thing with the Poisson. Another one of those things that I kind of, in 230, I'm like, oh, and then there's a Poisson and it works like this, and try one question and then we're done. The Poisson distribution. If you're dealing with counts, right, at some rate, then you're probably going to be able to map it back to a Poisson distribution. There's a couple of other ones, but usually you can kind of morph it into a Poisson situation. So the Poisson distribution is the frequency distribution of the number of events in sampled units of time or space. Oops, in sampled units. In sampled units of time or space. Often it's time that we're talking about, right? So if I tell you I work at a bank and I tend to see one customer every 10 minutes or so come in, right? Then if I run the bank, I can use that to model how many customers to expect, how many people to have working, right? That kind of thing. And so usually we're talking about time. So if we're counting events happening in some set amount of time, it's a Poisson. But it can also be space, right? The amount of defects in a roll of cloth, for example, every meter has some number of defects, right? Those are just some common examples. What we need for the Poisson is the lambda, right? The rate that these things happen. So the Poisson requires an estimate of the average number number of events per unit of time and or space, or should just say or, per unit of time or space. And that rate is the lambda. Lambda. Usually you're able to kind of look at previous information and you can get a pretty good idea about what lambda is. Or if you're, programming stuff, you can just try a couple of different lambdas, see if there's a difference, right? Usually if you change it, it's not going to change your results drastically. You'll have some idea, right? Lambda is somewhere between 25 to 35 units per square foot or something like that, right? And then you can try all those and get upper and lower bounds. Lambda is the estimate of the average number of events per unit of time or space. So that means that lambda is the mean. Is the mean number of events in a specified interval of time. Or space. What's tricky is that lambda, or I guess what's kind of cool, is that lambda is also the variance of a Poisson. So lambda is both the mean and the variance, which is kind of wild. Okay. This is where things get sticky. So because it's the average, it's the mean, but then there's going to be some variability as well, right? So we're going to have a good guess at how many events to expect, but then there's an average number of events, but then there's also the variability, which happens to be the same. It's like, yeah, it's pretty weird, but that's how it is. Oh yeah, this is where it gets a little sticky. So now the exponential distribution is, in my mind, a little bit similar to the Poisson, except now it's the time or distance from one event to the next event, whereas the Poisson was taking some interval and looking at how many times things happened, right? Counting how many times, but now we're looking at the time between these events, and that's the exponential distribution. Exponential distribution is the frequency distribution of the time or distance from one event to the next event. From one event to the next event. Yeah. The exponential distribution, right? You might remember tends to look something like this, right? So it increases as time passes. And so if the rate that things happen with is constant, then as more time and time passes, then it's more likely that that event will happen eventually, right? And so here I am going to say that the exponential can be used to model things like time until failure, but only if the lambda is constant, right? Which is not necessarily true. If we're talking about a machine and we're talking about time until failure, how long is it going to take for this machine to fail? Well, the average rate that things kind of fail at, right, is going to change over time. Parts get older, and so then they break faster than they do if they're new, right? So this isn't always the case. Don't worry, we've got a solution. Yikes. The exponential can be used to model time to failure if lambda is constant. I guess I should say the exponential distribution also uses lambda, right? Because they are related. The Poisson and the exponential, the Poisson counts how many things happen in a certain amount of time. And now, how long is it going to take until the next event? They'll rely on the same thing, but the exponential distribution also uses lambda, which is the rate from the Poisson. The exponential assumes that lambda is constant, which is not necessarily true, right? But then if we've got a large interval of time, what we can do is we can break up that interval and we can look at, okay, well, lambda seems to be constant for the first 2 years of a car, right? And then maybe 3 to 5 years, the rate of things breaking down maybe is constant or relatively constant. And then maybe we can break up that time period to have individual lambdas that are constant. So the exponential distribution assumes lambda is constant, which is not always the case. Oops. In those instances, when it's not constant, right, then we can break up the interval where we can assume that the lambda is constant, and then we can change the lambda over time. It might be reasonable to break up a large interval with non-constant lambda into smaller intervals with constant lambda. So that's one way that you can get around that. So lambda, huh? How do we get that? A lot of things we have a pretty good idea of what lambda can be, right? And so estimating the failure rate, which is lambda. Well, I can't remember if that's a section actually, but good enough. So in a lot of applications, we're going to have background knowledge and we can just approximate lambda from prior data. So in many applications, we can approximate lambda from prior data. What if we're estimating, or if we're talking about rare events, like very, very rare, planes crashing, for example? We're not after that, but we are very interested in trying to model that, right? Trying to avoid it, right? Prevent it. So then if we don't have a lot of data to work with, then we can kind of pick some values and we can model those or simulate with those values for lambda. So when considering rare events with very little data, we can make guesses and simulate outcomes to estimate the threshold values for lambda. And simulate outcomes to estimate threshold values for lambda. Oh, that looks like an X. Last but not least is that pickle, the Weibull distribution, which we did not talk about in Stat 230 because, well, it's crazy. But it is useful for a few scenarios. Okay, so especially because it lets things shift over time. So essentially what would be lambda, it lets it shift the lambda over time. So that's useful, makes it harder to deal with, right? But let's just talk about it here. So we later on will remember it exists, Weibull distribution, but we don't need to remember exactly what it is. Well, it's that weird one. The Weibull distribution is a generalized version of the exponential distribution. Is a generalized version of the exponential distribution. Okay, the exponential distribution was the one that was modeling how long it was going to take between events. Where the event rate, which is lambda, is allowed to shift over time or space. Oops. Over time or space, but usually it's about time, right? And so mechanical failure, right? We're letting these parts grow old. And so then we have to change the rate that these things fail with, right? So for example, mechanical failure. Or in general, time to failure analysis. Lots of money in that, obviously. When is this thing gonna break? So the Weibull requires a shape parameter, which we're gonna call beta. And it depends on if the probability increases over time or maybe it decreases over time, right? So the Weibull requires a shape parameter. Beta. And if beta is greater than 1, then the probability increases over time. And if beta is less than 1, then the probability decreases over time. We don't have lambda anymore because lambda has to be constant, right? And so we use something called eta, which is like a big fancy n, as the characteristic of life or the scale parameter. So let's see if I can keep this all on this one page here. I'll need one more line. For time to failure models, we do not use lambda. We use this kind of fancy n, which is eta, as the characteristic of life or characteristic of life scale parameter. As the characteristic life or scale parameter. All on one page. Okay, I went 1 minute over, so I'll owe you a minute on Tuesday. How about that? If you have any questions, let me know. Otherwise, have a wonderful long weekend. I'll adjust those due dates. If you've already done them, take a break. And I'll see you on Tuesday. Oh, should end this recording. Hey, look at you guys. Thanks, guys. Oh, sorry, Darnpreet, I'm just seeing your message here. Just from the assignments. You can use the assignments for practice. I've only given you one for chapter 1 though.
So when will be your first test?
That is a great question. This isn't you guys. It's on our Moodle page, hang on. October 18th. Test 1. I gave myself, mostly myself, a buffer day where we'll do some review. But I might need to use it for
Chapter 3, right?
up to and including chapter 3. So we just finished chapter 2. And then we'll do chapter 3, which is going to take us probably 2 weeks. So next week.
So it will be same as stack to 30 multiple choice?
Yeah, a lot of multiple choice, but not all multiple choice. And I guess, I don't remember. Oh, stop this recording.